Did you know that according to a recent report by Mavener, misconfiguration is the leading cause of cloud data breaches? Another study by Positive Technologies found that 1 in every 3 successful attacks on 4G networks is caused by faulty equipment configuration. In the context of commercial and open source software, a researcher found that misconfiguration accounted for 31% of server downtime issues, compared to 15% for software faults. These statistics are relevant to the study of ORAN systems, which is supported by open source software and cloud computing. Furthermore, most existing 5G deployments primarily follow the non-standalone approach, indicating a reliance on 4G infrastructure. Hi, I'm Asim, and today we'll look at how AI/ML can be deployed to solve such problems and how ORAN firms can further their business using this technology. Well, let's first understand what is Open Radio Access Network. While a traditional RAN architecture looks something like this, you may ask, how does ORAN look like? The main difference is that the BBU pool is further split into DU and CU using virtualization technologies such as network function virtualization or containers to deploy the CU and DU over servers. Here, CU is further towards the core network, resulting in a new interface called mid-haul. The distributor unit runs the RLC, MAC, and parts of the physical layer, while the centralized unit handles the RRC, the PDCP layers, and STAP in case of 5G. While traditionally, RAN is closed network, as RU, DU, and CU, which are all part of the RAN, must be bought from the same vendor, the ORAN Alliance has specifications to open the interface between RRU and DU and further between the DU and the CU. This means that a customer can mix and match the components from different vendors without being locked to one vendor for all these 3 components, thus resulting in an open RAN network. A question arises, who or what controls these components in an efficient manner? Well, the RAN Intelligent Controller, which is the central component of the ORAN, is built for that purpose. The general architecture can be seen here, and here is how it fits in the ORAN architecture presented by the ORAN Alliance and 3GPP. The RAN is connected to the 5G core to the next generation interface. The RIC is divided into 2 parts, the near real-time RIC and non-real-time RIC that handle RAN resources on millisecond and second scales respectively. In short, the near RT RIC uses XApps or third-party apps to control the CU, DU, and RU, whereas the non-RT RIC, located inside the service management and orchestration unit, is in charge of the long-term objectives in the RAN. The non-RT RIC does this by using RApps, which are also third-party applications that build policies to operate XApps over the AI interface. There are 2 ways that AI/ML can be deployed in the RIC. First is a single deployment option, where the AI/ML model is positioned within a specific component of the ORAN system. Aside from XApps and RApps, the RIC platform functions, as well as the CU and DU, can serve as hosts for AI/ML models handling complex processes. In the distributed deployment option, the AI/ML models are distributed across various ORAN components. For example, in model splitting, some layers of the artificial neural network might be assigned to the end device user equipment, while the remainder of the layers are placed in the RIC application. The cooperative effort of NetAI and VMware, where they demonstrated their energy-saving RAP, is an example of such AI/ML collaborative work, but nothing specifically related to the misconfiguration detections. Well, where does AI/ML for misconfiguration detection come into the picture? Misconfiguration is defined by NIST organization as an incorrect or suboptimal configuration of an information system or component that may lead to vulnerabilities. One cause of misconfiguration might be an XApp failing to adhere to standard procedures when interacting with the E2 service models, resulting in its malfunction within the system. For example, under the aspect of integration, enabled default ports, services, accounts, and privileges can cause significant misconfiguration problems, and similarly, under the aspect of security functions, conflicting policies, and so on. How can AI/ML be used to solve these misconfiguration problems? Some AI/ML techniques which can be employed are shown here. Let's look at the first 2 methods. In active monitoring, this strategy involves interacting with the system by sending synthetic service requests or probe packets to uncover any misconfigurations within it. In contrast, the passive monitoring method involves the study of system elements without the use of probe packets. These solutions often employ sniffer tools for real-time telemetry and KPIs. There are a number of commercially available tools that offer misconfiguration detection. Their documentation indicates the use of both passive and active monitoring to identify integration and security function misconfigurations. Detection tools for other misconfiguration issues have yet to be developed. Note that none of the existing open source or commercial near real-time RICs have incorporated a conflict detection and mitigation solution. I consider that experimenting with this approach of conflict detection among XApps in an ORAN testbed and the other AI/ML techniques could represent a significant milestone in the field of misconfiguration solutions. This will promote the development of multi-vendor XApps for optimizing RAN operations, while also guaranteeing reliability and minimizing outages for ORAN vendors and ISP providers. In conclusion, there is scope for R&D in this subject since ORAN is such a developing field. Mitigation methods can be deployed and developed by utilizing AI and ML. Therefore, any ORAN vendors or ISP providers can be one of the first companies, if not the first, to develop and or utilize such solutions.